Hey everybody, today we're going to be going over a brief introduction and tutorial of SAP2000, the structural analysis tool. It's a fairly common tool that's used in practice a lot, and it's a good tool to know also for academic purposes, which is how we're going to be demonstrating it. So the first thing you'll need to do is first download SAP2000, obviously, and also download AutoCAD. I'm going to be demonstrating how to use SAP2000 and importing geometry from an AutoCAD.dxf file and how to set up a model from there. I encourage you to follow along with this tutorial at your own pace. Feel free to pause the video as we go along and follow along with the steps just to familiarize yourself with the process of creating and setting up models. So without further ado, let's get started. So the first step in creating a model in SAP2000 is to first define the geometry of the problem you're going to actually model. And I'm going to do this in AutoCAD, and I'm going to consider just a very simple two-dimensional geometry. You can do all the same steps in 3 dimensions, but I think it's more illustrated to do 2D first. All right, so to get started, open up AutoCAD, create a new file, and then from there go to layer properties, and let's just start by creating a couple of layers. I don't know, we'll just leave them as their default names, layer 1, layer 2, maybe we'll add an extra layer here as well. And just to distinguish between them, you can also add some colors. Doesn't really matter what you choose, at least for the purpose of this tutorial. The intent is to demonstrate that you can go about creating models in AutoCAD that are defined relative to multiple separate layers, and we will distinguish between members that all have the same cross-sectional properties and all of these other things based on which layer they belong to. So for example, maybe layer 1 just consists of all the structural members that will be assigned, I don't know, the cross-section properties for, the heavy-duty members, and then maybe layer 2 will be, the less heavy-duty members, but somewhere in between, and so forth. So to start off, let's just kind of draft a very simple example of a structure that we're going to model in SAP2000. And to make things simple, let's just consider a very basic two-dimensional truss. So to start off, let's consider, I don't know, equilateral triangles in a planar truss configuration. So to do that in AutoCAD, just a refresher, let's define some lines, maybe a few straight lines, and then define an equilateral triangle by basically forming something like this. All right. And then we can proceed in just kind of duplicating this structure multiple times by using the copy command. I prefer to use keyboard shortcuts in AutoCAD, but you can do it however you like. And there you go. A very basic two-dimensional truss. However, as I said, let's maybe diversify the types of structural properties that we're going to assign to each one of these members. So as I said, let's let layer 1 be the heavy-duty members in the structure, members that are going to be assigned larger cross-sectional properties. We'll suppose that maybe the top and bottom chords of this truss structure will be the larger members of interest, and then the webs, or kind of these intermediate members, we'll assign some different property. We'll say layer 2. Now to make things kind of interesting, let's add in some extra details for layer number 3, which will correspond to maybe smaller detailed members that kind of connect things together. I don't know exactly how we want to do that. Maybe that'll be these vertical members we'll add in. Something like this. You don't have to draw your structure exactly like how I'm showing here. Use your creativity in going through this tutorial. Maybe you'll want to design, some different representation. Who knows? But that's it. So we've created our model. Now we just need to import it into SAP. So now that we've defined all of our geometry in AutoCAD, we can bring it into SAP2000 rather easily by first creating a new project. So go to New Model. Let's just call it a blank model. And we can then import geometry from SAP by going to File, Import, AutoCAD DXF file. Now, If you're like me and you tried converting your AutoCAD model into a DXF file and going through this process, it didn't work for me. I actually had to go to the drop down, switch to DWG files, and then actually import the AutoCAD.dwg format. Selecting your file and then specifying a few parameters like what's the global up direction in your SAP2000 model compared to how it's defined in your DWG file. Set what the units are. These units should be consistent with whatever you defined in your AutoCAD file relative to whatever dimensions you specified, and then you can maybe leave these parameters alone. Just set them as their default values. It'll take a second as things load up, and then you'll be prompted to import whatever layers you have defined in your AutoCAD model into your SAP2000 model as different structural elements or members. In the case of this model, we'll treat everything as frames or one-dimensional elements, and we can select all of the layers for which we've basically defined our model in AutoCAD. So layers 1 through 3. Clicking OK. Now we basically have our model geometry imported into SAP2000. We can reorient our view by clicking through these set view options. In this case, looking at the structure at the XY plane or from different perspectives, as you prefer, in the XZ plane or YZ plane, respectively. So you'll notice all of our geometry is directly imported into SAP, and we can actually look at how these different structural members are grouped together by going over to the Model Explorer and then expanding on the Groups tab. You'll notice we now have layer 1, 2, and 3 all imported into the model. And if we go to select layer 1, for example, we can basically select all the structural members from our AutoCAD file. So another thing to note is that even if you drew your structural members such that there wasn't necessarily a joint connecting endpoints of a given member, new joints will be inserted at basically the connections or intersection points between lines in your AutoCAD model and the supposed structural members in your resulting SAP model. So there's a one-to-one correspondence most of the time between points you've defined in your AutoCAD file and basically joints in your structural SAP2000 model, as well as lines in your AutoCAD file to structural members or elements within SAP2000. Okay, so now we have everything in SAP2000 for our structural geometry. Next step is defining all the material properties and the cross-section properties that we're going to assign to all the members in our structure. So to define materials, go to Define, Materials, and then specify Add New Material. From here you can select from a bunch of predefined materials that are already in SAP2000, and this might be the easiest way to go about creating a new material. If you needed something different, you can go to Other and then specify the properties directly. But for example, if I choose steel with A36 structural properties, which is a fairly typical grade of structural steel, selecting OK, I'm done. I basically have created a new material that I can use and assign to all the members in my structure. If I want to find out more about what are the specific material properties assigned to this material that I've defined, I can go to Modify Showed Material and then go Modify Show Material Properties to look specifically at what are the modulus of elasticity, even things like what's the coefficient of thermal expansion, and potentially things like what's the yield stress of the material. You can look at it in terms of different unit systems as you prefer. In this case, in Newton meters centigrade, I see that modulus elasticity is what I would expect, close to 200 gigapascals. The next step is defining cross-section properties. This can be done by, again, going to Define, Cross-Section Properties, and we're going to focus mostly on frame sections. That's what we're going to assign to all of the structural members in our model. We can define new cross-sections by going to Add New Property, and then selecting from a bunch of different predefined structural shapes that commonly show up. In this case, also intending for this to be designed for a steel structure, let's look at a wide flange section. So we can initialize a new section. We can assign it a name. Let's call it section 1, intended to be assigned to layer 1 of our AutoCAD model. And then we can make some modifications according to whatever specifications we want to assign for the actual geometry of this cross section. So maybe let's make it a little bit shorter, for example, or maybe modify the web thickness to be a little bit thicker than what it is currently. There you go. You can get some very weird shapes by doing this. We can also define, let's say, the assigned material for this particular cross section, and selecting from the existing material that we made previously. Click OK, and we've defined now our first section. To actually assign our given cross-section properties to different members in our structure, we can do so one at a time, or more efficiently by assigning cross-sections to entire groups of structural members at a time. So what I'll advise is to go first to Select, and then go to Groups, and select whichever layer you intend to assign a particular set of structural properties to. In this case, layer 1. In which case we can select basically the top and bottom members of our structure. Okay. Once we've selected layer 1, we can then go to Assign, Frame, Sections, and then assign to those members in this particular group section 1. Click Apply, and you can see we've updated the cross-section properties assigned to all of those members in that group. Supposing that I've assigned all the different sections to my structure, I can verify which sections have been assigned to the model by going to the Display Options button and then selecting a few different options here. I can either look at the section labels for all of the members in my model to verify that the appropriate sections have been assigned to each one, or I could select the Extrude View option in the view type. The Extrude View actually provides you a graphical representation of which sections have been assigned by actually showing the cross sections of each individual member. It's a little bit easier to see if you look at it in 3 dimensions, in which case you can see that all of the top and bottom members have been assigned structural members with a cross section that looks something like an I-beam or a wide flange section. And to my other structural members, I've assigned either C-channels or, in the case of these vertical members, an L bracket or an angle member. So step 3 involves defining all the support conditions in your structure. To assign restraints to a model, select a point to which you intend to apply a corresponding boundary condition, a displacement boundary condition, and then go to Assign Joint Restraints. From here you can select how you wish to restrain this particular joint, either by constraining its translation in the X, Y, or Z directions, or constraining its rotation about each of those 3 axes. If you want to basically just quickly come up with the fast restraint application to each one of these, you can select from the preset options of a fixed restraint, which constrains everything, or a pin constraint, which only constrains translation in all 3 directions. If you assign a roller constraint, which only constrains motion in a particular direction, you should be careful about how you actually apply this, keeping in mind what your global coordinate directions are. Refer to your global coordinate directions when deciding which directions you want to actually constrain a particular joint in. In this case, I'll just choose a simple pin joint for the left support, click Apply, and to the far right joint, I'll assign a simple roller condition that constrains displacement only in the Y direction, or the 2 direction. Step 4 involves defining all the loads that you intend to apply to your structure, and this can be done in a few different ways. First thing, we need to define a load pattern before we can actually assign loads that correspond to a given pattern of applied loading to the structure. To do that, let's go to Define, Load Patterns, and then create a new pattern by specifying a name, we'll call it pattern 1. The type, it could be a dead load, which is a type of load that would be applied to the structure and basically stays there the entire time, or a live load, which might be variable. If it's a live load, the default is to not include self-weight in the actual loading scenario. We'll leave that as the default, create new load pattern, and we're done. We now have a new load pattern to which we can actually assign loads. The process of actually assigning loads involves either specifying point loads or distributed loads along members. To do that, let's consider applying a point load at this top joint here. Select this point and then go to Assign Joint Loads, Forces. You can also assign joint displacements as well. Then you can select the particular pattern to which you want this assigned load to show up. We'll select pattern 1. And then we can apply loads in the global X, Y, or Z directions, or concentrated moments as well. So in this case, we can apply, let's say, a vertical load acting in the negative Y direction. So we'll say minus 10,000 newtons. Apply, and you'll see that the load now shows up on our structure, acting in the appropriate direction. To assign distributed loads, first select all the members to which you want to assign a distributed load, and then go to Assign Frame Loads Distributed. From here, we can again select what's the particular load pattern to which we want to assign these loads. What's the actual direction of the applied loading? In this case, we'll select the Y direction, or the vertical direction for this two-dimensional structure. And then we can select what type of load it is. In this case, a distributed force load. If the load is uniform across all members, then we can just specify a uniform load. In this case, let's say minus 100 newtons per meter. Or we can assign trapezoidal loads, which basically vary at different intervals along the length of the member. To make things simple, let's just consider this uniform load. Click Apply, and we can see that now the distributed load is applied to these bottom members. So the last step is actually running your analysis and interpreting the results. Before we actually run our analysis, we have to make sure that we're setting up the model such that it will actually deform in 2 dimensions rather than in full 3 dimensions. To do that, go to Analyze and Set Analysis Options. Here you'll be able to select a subset of degrees of freedom that you want to activate or enable in this model. Since my model is defined in the XY plane, and I only want to actually represent deformations within the XY plane, I have to disable deflections in the Z direction, or in directions perpendicular to this plane that we're viewing the structure in, and disallow rotations about the X or Y axes. If we don't do this, then we'll get some error messages from SAP that'll tell us that it can't actually solve the problem. Once we've specified all the analysis options, we can run the model by going to Analyze and then Run Analysis, or also by just clicking the Run Analysis button. It'll prompt us to select which load cases we actually want to run, but if you just want to run everything, click Run Now, and it should run all the load cases for this model. Now we can visualize some interesting results. For pattern 1, the loads that we applied to this structure, you'll notice the deflected shape looks quite exaggerated. We notice that there's definitely some deflection downwards at the point of application where we've applied a load, and there's quite a lot of deflection happening in the bottom members to which we've applied this distributed load. You can examine specific deflection values by hovering your cursor over specific points in the structure to see how far it's deflected. In this case, not so far. SAP will amplify displacements in order to make them more visible. Just bear that in mind, that these aren't actually representative of the true displacements that the structure would experience. We can visualize what forces are in individual members by going to the Show Forces and Stresses button and selecting Frames, Cables, and Tendons. From there, we can select the particular load case for which we'd like to visualize internal element forces, and then select which force we actually want to visualize. Let's say we're interested in visualizing the internal moment measured about the 3-3 axis or the z-axis. This is the principal bending moment experienced by most of the members in a planar structure like this. If I click apply, you'll notice that you don't really see anything other than maybe some of the value labels that appear in this. This apparently is a visual issue that has to do with the way that SAP displays planar structures. To actually visualize in a more definitive way the moment diagram for each one of these members, go into 3D, and then you'll actually be able to visualize, as these diagrams show, the moment in each individual member. This concludes our tutorial. There are many other features that you could use in SAP 2000, but frankly, this is enough to get you started, particularly if all you're doing is simple linear structural analysis. At this time, I'll open it up for questions if you have any. No? Well, I'll see you next time.